Wonderful. All right, so we're gonna start with a little bit of review on just counting hydrogens and lone pairs for these molecules. So we don't need to do, you don't have to redraw it as a complete structure for this one. It's good practice to do that, but for now, let's just figure out what we already did aspirin and caffeine, so let's do Tylenol.
Okay.
And just count your hydrogens and lone pairs. So what's the trick to getting the right number of hydrogens? How many bonds is carbon gonna make, right? So if carbon's gonna make 4 bonds and there's 3 drawn, you need 1 more hydrogen. Any hydrogens missing?
Oxygen.
So oxygen has 2 bonds when it's neutral, right? So it doesn't have hydrogens, it has lone pairs. All right, how about the nitrogen? Any lone pairs or more hydrogens?
1 lone pair.
1 lone pair.
What about the carbon on the right side?
Yeah, we can't forget that's a carbon, right? So we've got a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. All right, when we look at this caffeine molecule, I guess we can do this with the acetaminophen too. The acetaminophen will work. What is the hybridization on the nitrogen?
sp3.
sp3's got 4 electron groups, right? So we would expect it to be sp3, which we would then expect to mean what as far as the shape, bond angles? We have 3 dimensions to work in, right? So 4 electron groups.
Pyramid.
Tetrahedral. So we would expect it to be tetrahedral, right? Which would make these bonds 109 degrees, and it would make the whole thing not planar, right? So this is another case of, I'm going to tell you, I taught you how to do hybridization. Now I'm going to immediately tell you that I didn't give you the full picture.
Okay.
That's what this whole lecture is. It's basically, when does resonance play a bigger role? Because if we actually look up that structure, when we look at that structure, it's not tetrahedral. The blue one is the nitrogen. And if we look at these bond angles, so this one, well, let me. It's struggling. It's closer to 120 degrees than it is to 109. And if we basically, the only reason that's not 120 degrees is because the hydrogen is smaller than these other things. So they're pushing each other out more. So if it's not tetrahedral, where is that lone pair? What is going on with the lone pair? Because the lone pair is the only thing we can't see, right? And we know based on just counting number of electrons, it has to be there.
Yeah.
So either the nitrogen doesn't have a full valence, in which case it should have a charge as well, or there's something else going on there with the lone pair. All right, and so this is kind of what led to some of the first work in molecular orbital theory, was this discrepancy between what you expect to see and what you actually see. And so if we do the same thing, what we actually see in a lot of these cases is that atoms with lone pairs, they don't hybridize the way we expect them to. All right, so again, here's caffeine. We've already done the molecular formula for caffeine. We went through and added all the hydrogens last time. But if we actually look at the structure of this, we would expect three of these nitrogens to be tetrahedral electron geometry, and we see instead that all three of them are planar. If we look at this caffeine molecule, all of those nitrogens that are part of the ring structure look more like their sp3. Almost exactly 120 degrees, right?
Yeah.
So that's weird. What's going on with that? But basically what it means is, the term we're going to define here in a few minutes is called delocalized electrons, which basically means that they are not stuck in one place and they don't act as a separate electron group. Because what made the lone pairs take up space is the fact that they were pushing away the other electrons and they were in one spot and pushing everything else away. These three circled nitrogens don't behave that way. So there must be something else going on. And as a result, we actually wouldn't say that they're sp3 hybridized, even though we can look at them and we can say, oh, there's got to be 4 electron groups. The fact that that lone pair is next to a pi bond. There's a pi bond here and a pi bond and a pi bond here and a pi bond here. All of those pi bonds are going to basically allow those lone pairs to act like they're not stuck in one place. It's going to allow them to be delocalized.
So is a pi bond just a double bond?
Pi bond is the second part of a double bond. Right? So if we looked at CO2, CO2 is going to have a sigma bond that looks like this, going both directions. So that those ones that can completely overlap are sigma bonds. And then in addition, the carbon has those unhybridized p orbitals that are going to look like this. And they're sort of going to smear out.
So the blue is the pi bond.
The blue is the pi bond, the red is the sigma bond. And a double bond is one of each of those.
Okay.
All right, so that's, you might hesitate to say a pi bond is a double bond. it's part of a double bond.
Yeah.
What would the pi bond look like on the other side? Can I just draw it in the same direction? Can I overlap another one like that on top? No, because those were unhybridized p orbitals that we took to make that pi bond, right? And p orbitals are what angle to each other, the different parts of the p orbital. It was X, Y, and Z, right?
Yeah.
So they were all 90 degrees from each other. So that means our other pi bond is gonna have to be 90 degrees from the blue one. Because we also have to have a pi bond over here, right? Between these two.
Yeah.
So it would be like either out of the board.
So it's becoming out of the board and into the board. If you can try and show that three-dimensional shape, you're better at this than I am. I stand too close to it. I think that's what I figured out. It doesn't like when I brush it with my elbow when I stand too close to it. Now I've confused it. All right. So the reason that this sort of weirdness occurs with these pi bonds and with these lone pairs is this. Minimize again. Is because of the difference in size between the electrons and the nuclei. All right, so those molecular orbitals, we just said, well, the electron's like somewhere in that space, right? But we can't really say where it is exactly because it behaves kind of like a wave because it's so small. The nuclei don't behave like that. The nuclei are pretty fixed in place relative to that. So that's actually what's called the Born-Oppenheimer approximation. Have you ever wondered what Robert Oppenheimer did to get put in charge of the Manhattan Project? You don't hear his name with Bohr and Einstein and those. He was a contemporary of Bohr and Einstein, but he was much more on the mathematical side. And so the Born-Oppenheimer approximation basically says we can treat the nuclei like they don't move because they're going so much slower than everything else. Think of flies around an elephant. If you're trying to model how the flies are moving relative to each other, you can basically assume that the elephant's standing still because the flies are so much smaller and so much faster. So with that in mind, though, that means that these electrons, they don't stay in one place and they behave like that wave. And what happens when you do that is it actually means that you can get these reactions that just look like a really quick instantaneous reorganization of electrons. And it happens so quickly that we don't even really say that, we don't say that it's happening, we say that it's simultaneous. Basically, the things are in both places at once. Right, and so the way that we first figured this out was in benzene. So benzene C6H6, y'all know the structure for it because you've seen it everywhere. But before, if you were taking a class in organic chemistry in say, 1910, all they really knew was that benzene has a formula of C6H6 and it's really, really stable. And if you pull a hydrogen off and replace it with a chlorine, you'll only get one product, which seems that seems easy enough. Say, okay, well, I can do something like this, right? Then technically all the carbons are symmetrical, and if I took a hydrogen off and put a chlorine there, it doesn't really matter which carbon I put the chlorine on, because they're all symmetrical, right? However, what they found is if you do a double substitution, you get 3 products. When you put the second chlorine on, there were only 3 places to put the second chlorine. Which means that it can't just look like this. Because if it just looked like this, we'd be able to say, okay, well, that carbon is distinct from that carbon. They're both adjacent to the first chlorine, but one is across a sigma bond and then one is across a double bond. And then same for these two, they couldn't be the same either. And then we have the opposite side. So if it just behaved like this, we should see 5 products, not 3. And they couldn't really figure out why that was the case. Until August Kekuli took that idea from the Ouroboros from Egyptian mythology. And he basically said that, well, what if those electrons don't stay in one place? What if those pi bonds are allowed to move? And so he basically said, okay, well, really what you have is an equilibrium where your pi bonds start in between, let's call that carbon 1 and carbon 2, and then they rotate to be between 2 and 3. And in doing so, the other electrons followed them around to make room. So you kind of created this sort of ring structure of alternating double bonds. So that was groundbreaking. That was really big, except for the fact that they couldn't explain why it didn't react the same as other alkenes then. And so what turned out, they found something that they were not expecting in the slightest. Basically, because of the fact that you had these 3 pi bonds chasing each other around in a circle, that made a really unique system that made it more stable than it should be. Remember, we talked about bond energies for alkenes, for the pi bonds, and we talked about how much energy there was. Basically, if you have 3 pi bonds in a circle like this, you get something that's way more stable than just 3 alkenes should be. And that makes it so it won't go through the same reactions. And so they called this idea resonance. They said that the benzene was resonating between these 2 structures. Which, I mean, it kind of makes sense when you think about it, because if I draw a benzene ring, if I just draw a hexagon, and let's say that I try and show a 3-dimensional shape here. So think about this as a hexagon coming into the board and out of the board. If we switch the color here, if we try and draw those pi bonds like we had before, let's say we've got one of the pi bonds here and the other phase of it is underneath. I'm not drawing the full figure 8s. But we kind of had those figure 8s in here as well, right? And then in between these 2, and then in between these 2, because we had pi bonds here as well, right? What the idea of resonance was basically saying, well, if this carbon's sp2 and this carbon's sp2, what's to stop the bond from forming between these 2 instead? because they both have those pi bonds pointed in the same direction and in the right phase. So what resonance really is it's sort of like taking all three of these pi bonds and smearing them out together so that you actually get something that looks like a donut almost. And then the out of phase version would be down below. Right, so you kind of get like the average of all three of those pi bonds in both of their states at the same time. And that's what allows it to be so much more stable, is that idea that, well, we could put our pi bonds in two different places. And the more you can let an electron kind of roam free, generally the more stable they are. The more delocalized the electrons, the more stable they are. All right, so let's practice with a smaller case. We're going to see if exiting out of the slideshow and going back into the slideshow will make the pen work the way I wanted it to. There we go. All right. So if we look at this atom here, it might help to, or this molecule, it might help to draw out the hydrogens. How many hydrogens are there on a carbon with a positive charge?
2.
Just the 2, right? A positive charge, any charge on a carbon means that you can't have 4 bonds. So a positive charge means that that carbon is actually missing a pair of electrons. If you remember going back to doing the Lewis dot structure for it, CH3 with a positive charge only has a total of 6 electrons. So a carbon with a positive charge can only have a total of 3 bonds, and then it's got a partially empty valence shell. So what is the hybridization? Let's start with the easy ones first. What's the hybridization on the alkene carbons? How many sigma bonds or lone pairs do you have? No lone pairs. It's 3 sigma bonds though, right? So what does the hybridization have to be then?
SP2.
SP2. What's the hybridization going to be on a carbon with a positive charge?
SP.
We've still got 3 sigma bonds, right? In no lone pairs. So it actually looks just like these ones. So it's also going to be SP2. Because if you remember thinking back to what caused the hybridization, we hybridized, we started with the lowest energy state and we mixed together p orbitals into it until we had enough hybridized orbitals to make all of our electron groups, right? If we have 3 electron groups around a carbocation, that means that only 3 of these got included and hybridized together. Basically, every part of a p orbital that you include is going to make those bonds a little bit higher in energy because it's like a weighted average. So we're going to have, if we have a carbocation, it's going to be sp2 because it's got 3 electron groups, and then it's going to have 1 unhybridized p orbital, just like carbons that are making pi bonds. So if they're all sp2, that means that all three of these carbons can actually have an unhybridized p orbital pointing the same direction. Right, the alkene pi bond, that's what we've seen before, but then this carbocation has an unhybridized p orbital just because we have an incomplete valence. And what that allows is for this structure to have three p orbitals, all pointed in the same direction.
So then do those hybridize together?
Exactly. So instead of having a pi bond and an empty p orbital, what we actually see is a bonding orbital that looks kind of like a 3-carbon pi bond. So instead of just having pi bond here and an empty p orbital next to it, it can actually react, and react again is the wrong word, but we'll define it a little bit better in a second. It can move these electrons over to that partially empty valence.
So this is what I'm envisioning is the, you know, the thing that you can, like boxers use that's hanging and it goes back and forth really fast and it just like, you just see the one.
A blur.
Yeah.
Yeah,
That's
exactly. That's a good analogy for it, but as always with quantum, our analogies are not perfect. It's like if it was in all of that space simultaneously. It doesn't actually flicker back and forth between these two, it's both of them at the same time. And I think here's another cartoony way of thinking about it. If we have a unit, we know unicorns don't exist, right?
How dare you? Yes.
And we know dragons don't exist. Again, I know, crushing souls.
Okay.
Neither of these two things are real.
It in your face, be like, look, it's real.
It's fair. Neither of these two creatures is real, but if you kind of averaged them out, you could get something that looks kind of like a rhinoceros, which is real.
Okay, very true.
So what these resonance structures actually are, it's not like it's jumping back and forth between unicorn and dragon so fast that it looks like a rhino in between. It's that a rhino has characteristics of both of these. Right, so the other example is like a prop airplane. If you think about the propeller on an airplane, it looks like it's in one space until it starts moving fast enough, and then it looks like it's a disc, basically. If you took a really fast picture, you could still isolate where it is at any given point, so it's not perfect, but we have to treat it like it's in that entire space. You can't stick your hand in and out fast enough to not get hit, even if you knew where it was at any given moment, right? So we treat it like it's the combined, what we call a hybrid. It's all of that space simultaneously. All right, and so we see this anytime we have resonance structures, or sorry, anytime we have Lewis structures that are both valid. If you have two Lewis dot structures that are both valid, where you don't need to move any atoms to get from one to the other, then really what you have is both of them at the same time. All right, so here's another example. If we're doing like a Lewis or a carboxylic acid, we'll look at acetic acid. This would be the way we would normally draw the Lewis dot structure for it. Everything's got a formal charge of 0. Everything's got a full valence. We use the right number of electrons. However, without moving any of the atoms or breaking any sigma bonds, I could rearrange these electrons a little bit. if these electrons moved up and these electrons moved over, we could have something that looks like. I'm gonna abbreviate the CH3 since it doesn't matter that much here. That looks like an oxygen with 3 lone pairs now. Then an oxygen with 1 lone pair and 3 bonds down below. Now that doesn't look as good to us because what's different about this one?
She only has spaces.
The oxygen has 3 spaces being taken up,
The carbon.
but also the carbon still has 3 in both of these, right? So the carbon's hybridization didn't change. But that oxygen has 3 bonds instead of 2. Oxygen wants 2 bonds to be neutral, to be stable, right? So if it's forming 3 bonds, it has a charge. What's the charge on it?
It has an extra. Right?
As an extra bond, has the same number of electrons though. It actually lost some of its electrons though by doing that, right? It had 4 that it owned outright, and now it has, so that gives this oxygen a plus charge, which conversely means that oxygen's gonna have a negative charge. So these are not equal resonance structures, but they're both possible. We would expect this one to be more stable than that one. But the fact that we can draw one just by moving 2 pairs of electrons and not moving any atoms, any nuclei, and we didn't break any sigma bonds, we just shifted a lone pair and a pi bond, means that both of these are valid. And if we look at the structure here, we would normally expect this oxygen, it looks like it's sp3 here, right?
It's not because you're about to tell us.
Because this version of it
It's
is sp2. So the fact that there's another resonance structure where the oxygen's sp2 means it's actually not going to behave like this. If we measure bond angles like we did before and we looked at how planar it is, we see that even though it's mostly in this state, it actually keeps that oxygen sp2 instead, so that it can be both of these at the same time.
But is that less or more stable?
The fact that this allows us to spread our electrons out more instead of keeping them confined makes
The whole.
both of them more stable than either of them would be otherwise. You don't see this happening with alcohols. Because if we just had that's an oxygen with 2 lone pairs, right? But there's no other pi bond around it where it can shift them. So, and I'll give you some rules for when you have resonance structures and when you don't, because that's the other part of your quiz this weekend is going to be how many resonance structures can you draw that fit these criteria? And it's tricky. You're not going to be good at it at first.
Okay.
And that's fair. That's fine.
Are we gonna have to draw out the structures or just say like how many?
I think it has you draw them out, but you really can't. It's like those constitutional isomers where even I couldn't figure out how many there were until I actually drew them out. Like you kind of need to draw them out to be able to tell.
Yeah.
It's easy enough to say that there's more than one, but to put an actual number on it is hard to do that without drawing it. Right, so here's a picture of what the benzene orbitals actually look like. You said they kind of look like a donut. Looks like one of those mochi donuts from TV Donuts, right?
Yeah.
But basically it looks like pi bond spread out between all of them. And that's what makes all of the carbons identical to each other. This idea that we really have all of our electrons spread out at the same time is what explains the fact that that double substitution of chlorine, these two carbons are identical to each other. It doesn't look like it because just like before, the way it's drawn, that looks like a sigma bond and that's a sigma and a pi. But if it's constantly rotating, then it's really not like a double bond and a single bond. It's more like there's 1.5 bonds in both directions. Because there's a resonance structure where all the atoms are in the same place. Just with the pi bonds flipped. So if you move this pi bond over and that pi bond over and that pi bond over, we get this. Which means this carbon and that carbon are the same. They're both equally have just as close a relationship to this first carbon that has the chlorine. All right. So what do we do with that? Well, first off, we can define delocalized electrons. I already kind of did, but basically any electrons that can participate in resonance that are either part of a pi bond that can move around or are a lone pair that's next to a pi bond, like we just saw with that carboxylic acid. In both of those cases, those electrons are delocalized because you can draw a different resonance structure. And so if we go back to, I don't remember the exact structure of the acetaminophen. There was an OH here, and then a nitrogen, and then look like that.
Yeah, and then there's a hydrogen. Yes.
Right, so we already said that this benzene ring, those electrons are delocalized. They're chasing each other around in a circle, right? But the fact that there's a pi bond right next to that also means the nitrogen gets to join in too. Because the nitrogen could move its electrons over. And then these electrons can move that way. So we can get a resonance structure that looks like a negative charge there. Everything else is the same. Positive charge on that nitrogen. Everything still has a full valence there, right? We have formal charges, so we wouldn't expect this one to be as stable. But we didn't empty any valences. We didn't make it super unstable to do that. We just shifted some electrons, and we didn't break any sigma bonds to do that either. This is why when we looked up the structure, that nitrogen was flat. It was planar because it was actually behaving like it was sp2. Because that lone pair is delocalized. So go ahead.
What about the double bond on the oxygen?
That would make sense then too, for it to be able to participate as well, right? If instead. If we went the other way. You do that as well, right? In which case we get something that's gonna look. So made another nitrogen with 4 bonds. So what's the charge on the nitrogen? It's sharing its lone pair when it didn't want to.
So,
Positive. What's the charge on the oxygen now? The oxygen had 2 lone pairs. And now it's got 3.
neutral now?
It was neutral before and now it has extra electrons, so now it's negative. So yeah, that delocalized pair of electrons actually means that this entire, they call this whole thing a pi system. Because you've got all these pi bonds over here that can do resonance structures with the lone pair, and then the lone pair can also resonate the other way towards the oxygen. If we actually did something similar to the benzene where we actually looked at the shape of these orbitals, we would actually see like a pi bond spread out over this entire benzene ring like we're used to, but then also extending to over the nitrogen, above and below the nitrogen, and above and below the second oxygen over here. And so that whole thing
All exists at once.
all exists at once. So we actually wanted to draw all the possible resonance structures here. We would need more space because we just drew two plus the most stable one. The most stable resonance structure is always going to be the one that doesn't have any charges. If you can set it up so that nothing has a charge, that's going to be the most stable state. But there's also all those other ones, and plus we can also just move these pi bonds around in here without creating any charges. So we're gonna have a lot of different ways we can arrange that. If I draw it really small, we drew one of them that looked like positive and a negative here, which then has another one where these electrons moved over and so on. And so we would get a negative charge here with the rest of the molecule still there. And then we can do that one more time, move those electrons over. So that's going to give us one that looks like the negative charge there, still positive. So this one is more than I would ask you to do on your own at this point. But to your point, which of these is the best structure? Well, they're really kind of all happening at the same time. And so the fact that we have 1, 2, 3, 4 resonance structures with charges plus one where everything's neutral, there's a total of 5 resonance structures that are all we call them contributing. They're contributing resonance structures, even though this one's going to be our most stable. So we call that one the major contributor. You can also think of the whole as it like a group project. You've got the person who does all the work, but then there's little contributions here and there from everybody else, right? And the final project is the sum of everybody's work, even if one person contributed more than everybody else, right? So that's what the major contributor is. It's the most stable. And then you mix in some of these less stable resonance structures and average everything out. I actually like that for defining major contributor. Your major contributor is always going to be the one that's the most stable. If you have two that are close to the same stability, they're about equal contributors, which is the Platonic ideal of group projects. You want everybody to be equal contributors, but it never works that way. All right. So here's the rules. We're going to go through these and do this example, and then we're going to take a break and we're going to do more practice. The whole second half is just going to be practice with these. So for resonance structures, if it's a valid resonance structure, we can only move electrons. That's that Born-Oppenheimer approximation, right? We can't move any nuclei because they're too heavy and too slow. We're never going to break a sigma bond to make a resonance structure. If you break a sigma bond to make a resonance structure, that's not just a resonance structure. Now it's a chemical reaction because you actually broke a piece of the molecule off. So we will see cases where that happens down the road, but we don't call that a resonance structure. if you're doing your resonance structures the right way, you're not changing how many electrons you have. So the net charge doesn't change. Which makes sense on that last example with the Tylenol. Every time the nitrogen had a positive charge, but then there was a negative charge that floated around moving from atom to atom, right? So this whole molecule was still neutral. Even though we had some formal charges because of positive and negative. So you will always see that your net charge doesn't change, even if you do create some charges temporarily. They should still add up to whatever the overall charge of the molecule is. The last two are a little bit trickier to wrap your head around. I mean, it's maybe not, but they're the ones where eventually we're going to see some weirdness happening. But electrons only move one bond away. You can't have a pair of electrons jumping from one side of the molecule to the other. And then this one goes back to our number one rule of organic chemistry. No carbons with five pairs of electrons, right? And nothing in the second row can have more than 8 electrons total. So if you've already got an atom with a full octet, a lone pair can move away from that atom, but you can't push electrons towards it. So for example, on our last So on our Tylenol here, if we started by pushing the lone pair from the nitrogen towards other things, right? Why didn't we have any that looked like that?
No,
Not really, but
counting too high.
counting too high. That would give that nitrogen 10 pairs of 10 electrons, 5 pairs of electrons, and we can't do that. So if something already has a full octet, you can move, if one of those pieces of the octet is a lone pair, you can move electrons away from that atom, but you can't move electrons towards it because it already has a full octet.
So if the oxygen in this case didn't have a double bond, could you move the bond from the ring to the nitrogen and then the lone pair from the nitrogen to the oxygen?
Yes, it would go to this carbon.
Yes.
But that was one of our examples, right? But it started with, we couldn't move those electrons to that carbon until these electrons moved first. Right, and again, with it all happening simultaneously, the whole before and after thing is a little bit hazy. So it's really all happening simultaneously, but the fact that you can arrange it that way. You could do that, but except then if you do that, you're gonna be breaking up a full valence here. You're gonna be giving this carbon a positive charge in order to do that. And we'll find out that of these resonance structures, in general, we're not gonna see resonance structures that break up a full valence. Because that's so unstable. We can move charges around, but not break up full valence.
Did this whole thing about them all being in place at once help contribute to the thinking of atoms as a cloud instead of the ring?
Yeah, this is flipped cause and effect there a little bit. The whole idea that the electrons existed as a cloud is what eventually led to this.
Okay.
So how recent is this then?
1920s. There's Oppenheimer's not that old, and we're still refining our knowledge of it because that's not that long ago, it seems. But there was sort of a renaissance that happened in the early 1900s. Despite World War I, there was basically the ability of the brightest thinkers around the world to actually physically get together in the same space or communicate pretty much instantaneously, kind of created a giant leap as far as how much research we could do, how quickly. So we went from like zero quantum really being understood in 1890 to the stuff that we're talking about here in about 30 years, because everybody was able to get together for the very first time. And up until that point, until about the 1910, you couldn't readily travel between countries, between continents.
This is the time I should have existed. Like I would have been smart and discovered all these new things. That'd be so fun. Riley should have existed in the 80s. I should have been here.
Well, it seems like that, except that this was still so groundbreaking at the time. You have the advantage of having had a whole year of thinking about quantum mechanics. If you were discovering that for yourself for the very first time, it still would be really weird and you wouldn't think that you did it properly. Like, there's no way this can be true. Like, that's the whole Schrodinger's cat
Right.
idea. Was Schrodinger was trying to show that you can't apply quantum logic to macroscopic objects because it's just nonsense if you actually try to apply the rules in the wrong setting. So they really didn't trust it. And you'd have somebody like Einstein telling you the whole time that, no, you're wrong, it can't behave like that. Because Einstein hated quantum mechanics. He really did not like the idea. He thought that there had to be something we were missing because random chance and waves cannot explain things. We still haven't found whatever he thought he was looking for with that. But basically he thought that there was another force operating behind the scenes that we couldn't measure, that so it wasn't actually random.
Like a God type of force?
Not necessarily, but like not all of the forces, the four fundamental forces interact with each other the same way. Like magnetism does not interact with gravity. And so it was more like, well, what if there was a fifth force that we just can't observe directly because it doesn't interact with any of the forces we're used to? So it's gravity, electromagnetism, which used to be considered two different forces until the 1800s when they showed that electricity and magnetism were two sides of the same coin. And then there was strong nuclear force and weak nuclear force, which are basically what cause nuclei to form and then break apart in nuclear reactions. They've also found, though, that those really aren't separate from electromagnetic force. So electromagnetic and strong force and weak force all come from quantum mechanics. If you know the rules of quantum mechanics, you can derive the rest of those forces. Gravity is the odd one out at this point. It doesn't interact with the other forces the way that we would like it to make the math simple. So you could make the argument that there's actually only two forces, because you could say that there's the electro-strong weak force and then there's gravity. But for convenience sake, we usually keep them as four fundamental forces. Just for the sake of like historically describing the effects. Like, yeah, technically electromagnetic and strong and weak force are all the same thing, but when we're talking about magnetism, we're talking about it on a different scale than if we're talking about strong force. So we still kind of keep them separate as far as describing them.
Well, it sounds like we're missing something, that if those three are so connected and gravity's just there.
Exactly. That's what Einstein and Hawking were looking for. So Einstein lived in a time, he was looking for a theory of everything, like the Stephen Hawking movie is titled Theory of Everything. Einstein thought there had to be something tying all the forces together and probably a fifth force to explain the way quantum randomness works. Hawking, by the time Hawking came around, they had shown that three of the four forces were connected, but they couldn't connect gravity. Hawking was trying to connect gravity to that. That still has not been done. So they call that quantum gravity. Quantum gravity is basically how do we tie gravity into those other three forces and make everything one unified force. They may or may not ever do that. And they might not actually be connected, but it still sure seems like it should be.
It should be, and I feel like the answer is how the Earth is, because like the whole crust and layer thing is a theory, but there's no way to like cut open the earth and be like, is it this or is there some
Yes and no.
happening?
Don't get bogged down in, so. You didn't have me for Gen Chem. But the difference between a theory in science and theory in common use of the word is they're not the same thing.
Right.
So a theory explains why something is. And then a hypothesis is what you actually test. You don't test theories. You test a hypothesis in science. The theory and a law are actually just as well supported in most cases. The only difference is that a law predicts what will happen and the theory explains why it happens. So in this case, the law might be this molecule is planar. And the theory would be because resonance allows it to be planar. Right? So there is that idea. Theories get revised more often than laws because we can add little corrections here and there. But we actually did have to revise Newton's laws of gravity when Einstein discovered relativity. We don't think of that like, well, it's a law, it's fixed, it doesn't change. We actually had to add a tiny correction term onto it to account for relativity. And if we didn't do that, then GPS satellites wouldn't work. Einstein was the one that said, well, if you start getting close to the speed of light, time moves differently. Newton was dealing with things that were all close enough to the same speed relative to each other that he didn't need that extra correction term. But the satellites moving around the Earth are moving fast enough relative to the Earth itself that you actually have to put in a tiny correction for relativity, because otherwise they'd slowly drift out of alignment, out of calibration. So the laws, natural laws are still, we can still add corrections to them. And that's what happens with scientific theories too. We don't usually disprove a theory, we add a correction to it. And that's because for the most part, the theories are so well understood or well supported at this point. It just might be like, well, we forgot this other variable that never occurred to us. And so that in terms of geology, that might be like the whole idea of plate tectonics. Continental drift existed as a thought before that, but they couldn't explain the why. Plate tectonics explained the why for continental drift. And so the continental drift is the law, and plate tectonics is the theory in that case. But that's enough. Well, there's never enough philosophy of science for my taste, but we should move to do this example. This is going to look really simple to the one we already did as a test. Is there a resonance structure? For acetate? So right now we have a stable oxygen. We have an oxygen with a -1 charge because it's got extra lone pair, right? Anytime you've got something with a negative charge, that means a lone pair. And the lone pair can move towards a pi bond as long as you then move the pi bond to make room for it.
Okay, it's just a line.
So after those electrons move, what changes?
The double bond.
We moved a pair of pi electrons towards the carbon, so we made a new pi bond over here. But in order to make room for that, we had to take away the pi bond that was already there. Ah. Oh, I had it on the whiteboard. So what we actually get then is, it looks kind of like the negative charge is gonna flicker back and forth between the two oxygens. And what we actually see when we measure this is that orbital, that pi bond orbital extends over all three atoms.
How many lone pairs do each of them have now? The one on the top has,
One at the top now has three,
the one on the bottom has two.
and the one on the bottom has two.
Where did the one from the bottom, it's on the carbon now, the carbon has charge?
The carbon,
Or oxygen.
so basically one of these lone pairs moved to the carbon to make a pi bond. We moved those ones over to make a pi bond, but then we had to make room by moving the other pi bond away.
There's still a pi.
There's still a pi bond,
But
it's
it's
just,
not a double bond.
does it go to the,
I just didn't get the second picture before the whiteboard decided to disappear, so.
sorry, it was gonna look a lot like this, except with more coloring.
You have one of the lone pairs goes to the carbon. One of the
But
double
I was
bonds
like,
goes
what
to the
happened to
oxygen.
this friend?
That
But
becomes
that
the
made
double
that.
bond.
Okay.
And so what this actually looks like as well is if we actually measured the charge density, if we calculated all of these orbitals out and measured the charge density, it doesn't look like there's a negative charge on this oxygen or on that oxygen. It looks like there's like half of a negative charge on both of them at the same time. Because these two are going to be equally stable, right? We had a negative charge on an oxygen, we moved a negative charge to another oxygen. So they're going to be equal contributors to our school project.
So then is that third one different, that one, than the first one you drew on the whiteboard one?
No,
Okay.
I was trying to draw it the same. I just had more space and different colors. All right, so when we come back in 10 minutes, here's a bunch of resonance structures or a bunch of molecules that have resonance structures with the arrows drawn for you. It's quick word about arrows. Chemists are picky about their arrows. We learned that with equilibrium arrows versus regular arrows, right? We're also going to be very picky. This arrow is not an equilibrium arrow. An equilibrium arrow means that you actually have things moving back and forth. This is a resonance arrow. So an equilibrium arrow, just to remind you, had two arrows pointing in both directions. That means if you actually grab the molecule at random, it's going to be one of those two states, but it's going to be in one of them, not both of them. So a double-sided arrow, a single arrow, double-sided means resonance. Oh, just you wait. Because the reason I came back to this one to double check on that, I've been meaning to mention that, I kept forgetting anyway. But curved arrows are not reaction arrows or resonance arrows. Curved arrows show where the electrons are moving. They're called mechanism arrows. Or electron pushing arrows. So a curved arrow, especially if it's red, but just in general, if you see a curved arrow, that's actually showing you where the electrons are going and coming from. So every arrow should be either a new bond forming or a bond breaking or both.
Can we go back to the AI image that you showed us on the first day to?
Well, look at that, because it does not look anything like that, right? This is what people struggle with the most in organic chemistry, especially the first term, is mechanisms and resonance.
Is there anything for just a straight one-sided arrow?
That's
That's
just
the
an
regular
arrow.
reaction arrow.
Ah, right.
So that means it goes to completion versus equilibrium. And then doing that means it's resonance. All right. So we'll come back and we'll practice with these and try drawing these. I'll let you try drawing them on yourself and then we'll go through them and look at them when we come back at quarter after.
You know if anyone's still doing the research to find the connecting?
The quantum gravity stuff? Yeah, it's a big field still. A lot of mathematicians, because they actually, it's kind of expected that there should be like a mathematical proof somewhere or like a different derivation for the laws of gravity that starts from quantum mechanics, is how they were able to, they call that process unifying the forces. They were able to unify strong force, weak force, and electromagnetic by basically doing a different derivation starting from quantum mechanics laws. So there's a lot of mathematicians and theoretical physicists are working on it from the like, okay, well, what if we started here and did this really elaborate derivation? Does that get us to Newton's laws of gravity? It seems like every once a year or so somebody says we found it and then nothing ever happens from it. So we'll see. But yes, there's still a lot of research being done in that area.
I need to talk to you about making batteries.
Okay.
Do you think it is a feasible thing that we could do in science club? That wouldn't be like super expensive, no one's gonna blow themselves up.
Are you trying to power something with it?
Yes.
That's
A
gonna be the
drone.
trick. So in order to power something like a drone, you've got to be, the batteries that you would have to make would have to be very efficient and light. There's a reason that lithium ion batteries get used for everything right now. It's because they're efficient, they're light and small, and they're rechargeable.
Like,
Right.
could we make those?
Probably not. You have to use hydrofluoric acid and phosphorus hexafluoride as the electrolyte instead of using water. You don't just use water in them. I don't think you could make a battery. We could make a battery that you could measure the current from, but we can't, but we wouldn't be able to actually make a battery, I don't think. Just because of the scale, trying to make it that small and light. If we were trying to power something like a golf cart,
You could make a big
we
battery?
could make a big one. We could make something that looks really similar to a car battery.
Okay, that could still be fun.
Yeah, that would be fun because it's basically making those galvanic cells that you did in your electrochemistry lab.
Right,
Except putting a bunch of them in series together. And you just have to be careful because that particular reaction involves concentrated sulfuric acid as part of the electrolyte. And then you have, I want to say the anode reaction is lead-2 going to lead-4, and the cathode reaction is lead-2 going to metallic lead. And that way you can switch back and forth and recharge it pretty readily. But that's doable potentially. Miniaturizing things turns out is really hard.
Yeah.
And the science isn't even as interesting because that's just engineering at that point. How do we make it smaller?
Still something I could propose to the group. Still be fun.
Yeah,
Do you have any other ideas of like chemistry related things we could do with people, get them interested? I mean, like,
know.
everybody's already kind of interested in science, but like a fun activity.
I know engineering club made rockets one year, all the way down to making their own fuel. So, and have you ever done those rockets where you like, go out to the desert and you push a button and it lights off like a little cylinder?
No, but I kind of really want to.
Those are super fun. You could start by buying them. Like you can buy them off the shelf for, I don't know, probably $15. You could, well, and then all you have to do is replace the engine in it. And then what the engineering club did with Bruce one year is they actually they made their own little fuel cylinder.
Oh, okay.
We just start with it on the street, people like mom and dad.
I know. Our
These
parents,
things.
Our mom always told our dad.
so our parents went to high school together and they were doing these and
And he was like a like he wasn't even in that class, he was just helping.
no, but he was basically supposed to go like measure where they landed, I
Yeah.
think. And so he was standing out there and she launched it and it
And they had,
landed
like,
like
the
right
metal-
next to his foot and like lodged into the floor.
Like 2 inches in the ground. I mean, it was like the 90s, it was like the metal ones, right? So like.
So the way they're supposed to work is that the cap is supposed to pop off and there's a
Yeah, the parachute
parachute
didn't come
inside
out.
it.
Yeah.
I did that when I was in, what, 6th grade or 7th grade. One of my teachers did the science unit where it was making rockets. And I hot glued the nose cone in.
You did.
On
On purpose?
purpose, 'cause I thought it was gonna be really cool. It was really cool. It lodged like 1.5 feet into the ground at the track.
I'd almost kill someone.
Nobody was that close,
Okay,
luckily.
okay.
It was like 2 inches for that.
Yeah,
Yeah.
cause he was expecting it to let the parachute out
Right.
and then it didn't. Okay, that could be fun.
Do we have any professors here doing research projects?
Not really. We're not a research institution. So if I do it, any research, it has to be on my own time. At bigger research institutions, basically, instead of having a teaching load, their teaching load is like one class a year. And the rest of their job is just doing research and writing grants and stuff.
So cool.
So we don't really have anybody doing research here because it would be a pretty big undertaking on top of all of your normal work. I think the only people that really do it are the people we used to have an English instructor who still wrote and published, but she was just writing poetry and short stories. She wasn't doing like research. And then Scott Lucas, our anthropology instructor. He still publishes in peer-reviewed journal articles. I guess I don't know when the last one was, but a couple times a decade.
Yeah.
So, but beyond that, I don't think so. His stuff is actually really interesting. He did a lot of work with Disney on themed spaces. So you know how they design the lines at Disneyland to have themes. He did a lot of work on the sociology of why that works and how to maximize those like positive feelings. So if you look at his office door, he's got a article on curated spaces or themed spaces. I don't remember what he called it, but it is interesting.
I'm coming with you? Okay. Where are we going?
Oh, no, where is?
Oh, no.
know we're like trapped. Because the
Yeah,
people next door have their door open, or have their door propped all the way open, so our door only opens so much. Gotta be really skinny.
I'm not sure it's gonna work for me. But see if I can move it.
Wow, there's a lot of honey in here.
Alright.
It's like a honey jelly.
Now that they make Uncrustable makers now,
Yes, you can make
You
them at
can-
home.
yeah, it's just like a little cookie cutter sort of thing, but it crimps the edges.
I want that. I'm gonna add it to my Christmas.
I've seen it, I saw that somebody do it on YouTube with, like, a ham and cheese sandwich.
You know,
That's actually not a bad idea.
3D print the thing to make it. Oh, probably.
Bet you could.
Might be-
Put Atticus onto that.
Yeah,
They'll have 3 different versions by the end of the week.
different shapes, different sizes.
Okay, so there's some that are like a cookie cutter, and then there's some that are like the egg cutters that are like the.
Mhm.
What?
Or like a tortilla press where it's like hinged. Yeah. Those are probably the good ones that cost extra, but
They're like $7.
is it? My partner's YouTube algorithm is really skewed towards like random meal prep stuff because we have kids. And so they watch me prepare a week's worth of lunches for my 16 children.
Those are always insane. I'm like, how do you afford that? Right?
Yeah,
You ain't in California, that's for sure.
it's true. All right, let's do some practice with these. So this one we already kind of did. Right, if we have that carbocation. The trick with these is to remember that a carbon with a positive charge doesn't have a complete valence. So you can move electrons towards a positive charge. Especially a positive charge on a carbon. And when we do that, our resonance structure is just gonna look like we broke a pi bond and made a new pi bond. So here's our new pi bond. This middle carbon is still neutral. Right, because in both cases, the middle carbon still has 4 bonds. But the carbon on the far left now, we took away one of its bonds. And by doing that, it means that we've got a positive charge on the other carbon now.
So that would be the answer, just drawing both.
Just draw both of those. So for B, looks really similar, right? Except it's a negative charge on a carbon. And a negative charge on a carbon means a lone pair. A positive charge on the carbon and a negative charge on the carbon both mean only 3 bonds. But the negative charge means that you have a 4th electron group as a lone pair. And a positive charge means you are missing an electron group. So in this case, instead of drawing the chart, the lone or the pi bond moving towards the other carbon, we can't draw the pi bond moving towards the carbon with the charge because it already has full valence. So the arrows are just reversed. And it takes 2 arrows with a negative charge. It's gonna have the same net result though. You moved your pi bond from the left side to the right side, and you moved your charge from the right to the left. So again, to get full credit here, the arrows are already drawn. All you would need to do is draw that. The tricky ones are when the arrows aren't drawn and it says, draw all the resonance structures, all significant resonance structures. But we'll build up to that.
Do we have to draw the lone pairs?
It can be helpful. In this case, no, I would not, I just circled an answer and said it was right, and I didn't have my lone pairs drawn. While you're still getting used to how the charges work though, it's not a bad idea. So for C. Anybody remember what this type of functional group is called?
Yeah.
Well, so there's the ketone, but then does the extra oxygen make it something else? It's a anhydride? Maybe?
No,
No?
that would be if it was attached to another ketone on it, or another carbonyl on this side. It's an ester.
Mhm.
Alright, so if we draw these arrows, or if we draw the consequences of these arrows. Lone pair moves over, pi bond moves up. So we broke a pi bond. One of the things that can be helpful with these is you can always put everything back into its original spot. Because we know we're not moving any nuclei. And then we just have to worry about, okay, well, what happened with the pi bonds and the lone pairs? So a pi bond moving over towards an sp2 carbon is, sorry, a lone pair moving over towards an sp2 carbon is gonna make a new pi bond. And we had to move the existing pi bond up to become a lone pair. In order to do that. Say that again?
So 3 lone pairs.
So this oxygen now has 3 lone pairs.
It's 1.
The other one has 1. So what charges do we have on anything?
Is the top oxygen negative?
No.
Correct.
No.
Because it owns 7 electrons and it only has 6 on the periodic table, right? And the charges have to add up to 0 though, right? So what does the other oxygen have to be? Has to be positive.
It is.
And it is, because if we do the same thing, it only owns 5 electrons outright.
A little check that we're doing it right.
Right, exactly. These arrows look really similar to the one right next to it, right? The actual atoms are different. So we took a lone pair. We moved it over to make a pi bond. And in order to do so, we had to break a pi bond and give the nitrogen 2 lone pairs. So again, it looks really similar to what we did here, but the charges are going to be different now, right?
Yeah.
What are the charges going to be?
Is the carbon positive?
It's more positive than it was.
Okay.
How many bonds did the carbon have here? If it was a negative charge with a lone pair, there was also a hydrogen there, right? That we didn't show because it was a skeletal structure. So that means that hydrogen is still there.
Oh, okay. So it's
neutral now. What about the nitrogen? The nitrogen was neutral, but now
Now it has
has
one
more
more.
electrons. Yeah. So a net result of drawing these resonance structures, anytime you start with a charge, if you draw a resonance structure, you're basically gonna alternate atoms. Your charge kind of skips around. In this case, we started with the negative down below, and our resonance structure puts the negative sort of 2 bonds away. But the trick with that is to remember, it's not like these electrons are actually jumping onto the nitrogen. It only works because we can make this sort of chain reaction, where we move a lone pair over and then move a pi bond over. Right, so we're still not breaking that first rule of electrons can only go 1 bond away. The net result looks like the negative charge skipping around, but it's actually a different pair of electrons each time. All right, so let's look at some common patterns. Because these are gonna be basically your red flags that, hey, you probably have a resonance structure. So one of the ones I already mentioned is anytime you have a lone pair adjacent to a pi bond. And they call that an allylic lone pair. Allylic basically means 1 bond away from a pi bond. Because if we have this,
And these are common resonance structure patterns?
yes, yeah, these are structures that will pretty much always have a resonance structure. Right, and if you think about it, the ones that I used as our starting point, the caffeine and the Tylenol, that was this pattern, right? It was a nitrogen lone pair, 1 bond away from a pi bond is what allowed us to make those resonance structures. I want to be clear though that if you have something like this, that lone pair on the nitrogen is not 1 bond away. It's on the same atom that's already part of a pi bond. That doesn't count. That's not allylic. Right? Because this nitrogen already had, even if we had, let's say we were looking at this molecule here. That nitrogen's, the pi bond can resonate. You can move these bonds around just like benzene, but the lone pair can't. Because the nitrogen already has a pi bond that's part of this resonance structure, right? So you'll never have an atom that has 2 pi bonds both participating in the same resonance. Right, because the pi bond is into the board and out of the board here, right? And the other p orbital then has to be perpendicular to that. And so you can't have 2 sets of electrons both in the same pi system from the same atom, because this has to be 90 degrees away from the pi bond. And so it's basically you can't get any orbital overlap if it's 90 degrees away.
Since the pi bonds are into the board and out of the board, there's 4 of them. I mean,
Great.
like on one.
Oh, there's
triangle,
4.
Like there's 4 bridge things on one double bond. I'm just trying to think
Like
what way those go. Do they go like from the end to the C, like from the top end of the double bond to the bottom end of the double bond, or do they go from like the left to the right?
They're gonna go, they have to be in phase. So remember that when we draw those p orbitals, there's one side that's shaded and one side that's not, or one side that's red and one side that's blue. Basically, it's like a wave being up and down. They have to be in phase in order to line up. So you can only really have, you're gonna have. So just for basic molecule, the pi bond is gonna look like two p orbitals. A p orbital from this carbon and a p orbital from that carbon, sort of smeared out. But this whole thing is a p orbital. Both the shaded part and the unshaded part are both part of the same orbital. So if I go back. This is not the best example because it involves resonance now, but the fact that blue and then, the blue and then the red are part of the same orbital, but with the different phases, like shaded versus unshaded. If we're talking about things being in phase and out of phase with waves in the physical universe, we use up and down usually, like waves on an ocean, right? We can't use up and down to indicate phase here. But we also can't use like plus and minus because it's not like the charge is different. It's this whole other variable that we think of. It's kind of behaves like a wave being up and down, but in 3 dimensions. And how do you draw that? Well, you can do shaded and unshaded, or you can do 2 different colors, but it's part of the same orbital, part of the same wave. That kind of get at what you were asking?
Really what I was asking.
Yeah, try again. That's interpreted.
I just am wondering how it looks like with. I don't know how to explain this. Like, I don't understand if there's like, you have your pi bond, is it like your 2 things are in phase like coming out of the board like this, or is it like they're in phase like across the bond like that?
The second one.
This one,
Well,
kind of.
sorry, they're out of phase across the bond. So
Right, but not like down, they're like across, like bridging.
yeah, let me try and show it in 3 dimensions a little bit better. So if we draw the bond, let's just say we're just looking at ethylene. If we draw all the sigma bonds in the plane of the board, then the pi bond is gonna, one phase of it is gonna be sticking out of the board, and one phase is into the board. And the overlap is gonna be, so if this one is coming straight out of the board, and then there's the one behind it that's into the board. Those are both the shaded ones into the board. And so those will overlap with each other. These ones that are unshaded that are sticking out towards us, they're gonna overlap with each other as well.
And all of that is rotating.
And then all of it, so that is if the molecule was flat like this. If I took the molecule and rotated it, so now the hydrogens are coming out towards us and going back away from us. Your sigma bond is gonna be right here in the middle. So now it's shaped like this, right? Your pi bond is gonna be in the plane of the board. It's gonna be perpendicular to where these other bonds are going. So if the other bonds are straight in and out, the pi bond is gonna be straight up and down. And if this is the shaded part and this is the shaded part, this is what's overlapping. And this is what's overlapping because they're the same phase. Does that help you visualize it a little bit more?
Yeah, because I was just trying to visualize it, and it's like, so now I get it, because it is the 2 lines kind of when you're visualizing it.
It is kind of, yeah.
Yeah, I was just trying to figure out which way.
So to go back to this example, these pi bonds, if the ring structure is flat, the pi bonds are making that donut shape above and below. Or in front and behind, rather. But that means that this pi bond is planar. because this nitrogen's sp2. Those pi bonds or those electrons can't resonate with these other pi bonds. Because you can never have more than one pair of electrons from the same atom in the pi structure. So because this nitrogen already has a pi bond that's resonating with these others, the other lone pair is still stuck right there. And on the flip side, if we had something like this nitrogen has a lone pair. And now it's adjacent to a pi bond, not part of a pi bond. So this one can resonate. This lone pair can resonate where that one can't. And so we'd say that this nitrogen's lone pair is localized because it's stuck in one spot. This lone pair is delocalized. Because we can move it towards these other carbons and make resonance structures. Good? Take your time, you're fine.
Yeah.
So here's a bunch of common examples. I'm not going to go through all these right now, but these all have those allylic lone pairs. Lone pair, one bond, pi bond. Lone pair, one bond away from a pi bond. So they're all going to have the same general structure for their resonance structure, right? Move a lone pair towards a pi bond, move the pi bond to make room. So like that, or like that. No, I said we weren't gonna do these. I'm just gonna go through them fast since I already drew the arrows up there. Yeah. All right, so that's the most common one. But here's the other 5. This is gonna be what you're gonna come back to a lot in the quiz this weekend. This quiz is a little bit longer. Because I want you to both learn your functional group names again, but then also try and do some practice with this. It's got some where it gives you the curved arrows and you have to draw the structure, and then some where it just says, draw all of them. So allylic lone pair, allylic carbocation, because that allylic carbocation, I'm just gonna reiterate, allylic means not part of a pi bond, but one carbon away from a pi bond, or one sigma bond away from a pi bond. So if it was an allylic carbocation, there was room to move the pi bond over. That was another one of our first examples, right? If you have a lone pair adjacent to a carbocation, that'll do the same thing, right? Because a lone pair can move over and fill that carbon's valence shell. here's the benzene example. Conjugated pi bonds enclosed within a ring can basically ricochet around that ring endlessly. Way my first OChem instructor described it as it's like having 6 magical ponies in a corral. They're just gonna be very happy and chase each other in circles forever. Might not land as well since you actually have experience with horses, but the idea of they're gonna continuously be moving in a circle, kind of alternating where is the pi bond, and it's really all of those places simultaneously. Which is why the other way that you see a benzene drawn sometimes is a hexagon with a ring in the middle. Because that's basically indicating that you have those alternating pi bonds. Then this one doesn't happen as often. If you have a pi bond between 2 atoms with different electronegativities, you can just get the more electronegative element just sort of ripping the electrons away from the other one. We don't see that very much because then that's gonna make something that has got a negative charge right next to a positive charge, and that positive charge is not a full valence. So that's not gonna be as stable, nearly as stable as having them actually form the pi bond. The last thing I want to talk about in 3 minutes. I'm not going to grade this one particularly harshly because you're seeing it for the first time now. If we're trying to rank how important the resonance structures are, if we're trying to figure out what the major contributors are, we're always going to look for, okay, are some of my resonance structures more stable than others? And so the most important factor is if we can fill all the octets. If you have one resonance structure where everything has a full octet and then one resonance structure that doesn't fill all the octets, more filled valences is better every time. If you have 2 resonance structures and they both have all the same number of valences filled, the next most important thing is, can we get all the formal charges as close to 0 as possible? If we have to have a negative charge, putting it on the more electronegative element is usually preferable. And so these are in order of importance. The most important is the first one. We're down in 3 and 4. 3 especially, we're splitting hairs. So in that last example where I said, oh, we never really see this. That oxygen has a negative charge and it's more electronegative. Seems like it's a good thing, right? Except for the fact that in order to make this one, you had to break up a full octet. Because this carbon no longer has a full octet, and that's more important than putting a negative charge on an oxygen. All right, so for the quiz this weekend, there's one of the questions that just says, here's a molecule, draw all significant resonance structures and rank them in terms of importance. That's going to be a reach for you this weekend. Especially starting from a blank piece of page. So check the recording that I will remember to put up this time. If you don't see the recording when you're working on the quiz, then I may have forgotten. So just shoot me an email to remind me. But I'm gonna go down to my office and do it as soon as I can. But don't panic. And the auto grader is basically turned off for this quiz because it's all going to be like upload a picture of structures you drew. So give it your best shot. We'll go over the answers on Tuesday. And we'll go from there. All right. Good job this week and have a good weekend.
Do you know if there's a class that's here like right after this? Cause I kind of want to finish this right now. It's only gonna take me like not that long, but I want to make sure no one walks in, it's like, what's going on?
You got at least an hour because they try not to schedule any classes between noon and 1 on
Okay.
Tuesday,
There's
Thursday.
only one lab that happens.
Right.
Right.
Okay, I'm
So
good.
you got at least an hour.
I will take that.
You feel